for a moment so when you open this up, you can see it. The reason we have theorems is so that those of you going into Calc 2, Math 70, and so forth, the professor there may decide that he or she wants you to go through some proofs of some calculus theorems, other theorems. And they may go back and take a look at some of these, and I want you to be aware of them. We're not looking at any proofs of these as such, but they are nice to know that the ideas are substantiated by some theorems here. And I'm not sure where the top of this statement is. There it is. Okay. So it has a name, and I'll just pull that down so we can see it. Now, basically what we have here, and I'm going to highlight this, it may have gotten lost in the brackets, it's the natural log of the absolute value of a function. And the reason I know that it's a function is because the variable of differentiation is x, but this is not x. And so that tells me that it's a separate function. So it's a composite function here. The inside function is u, and the outside function then is the natural log. Well, just a word about this absolute value. If we have the absolute value of a quantity, and I'll just make it a, we know that that phrase has a value, has some numerical worth to it. And because most of us don't compute well with logarithms, but we do compute very well with exponents, we're just more familiar with them, we can always go back and look at this in a more familiar way. So the value over here is an exponent, but what's the base of that exponent? We're talking about the natural log. Someone said it. E, yeah. So that we have e to this exponent is equal to a. Now, if that is true, then I'll give you even an easier one. How about 2 to a power equals a? Is there any way possible for this quantity over here to be negative? Can a ever be negative? If you know exponential, you know that it won't even be 0. It's always going to be a non-negative, a positive quantity. So what if, and this is going to be one of our examples here, but what if I had, let's say, the natural log of x squared plus x minus 2? Are you guaranteed that x squared plus x minus 2 is always a positive quantity for any and all inputs? No, we're not. And so if I put the absolute value signs around it, now I'm guaranteed that. And so that's basically what this theorem is talking about. What if now I want to take the derivative of this function? So if I take the derivative of this function, then the inside function is x squared plus x minus 2, and the outside function is natural log. And we talked about how when we take the derivative of the natural log, we take 1 divided by the quantity, and then we multiply by the derivative of that quantity, and that's exactly what we're saying up here. This is the quantity u. We just have 1 divided by that, and then we take the derivative of the inside function. So just keep in mind, this is representing an inside function right now. Okay, so that's why that's there. If it were negative, if this had a negative value to it, it would be an undefined expression, because you cannot take the natural log of a negative quantity, because you can't take e to a power and get a negative quantity. Okay, so with that understanding, if we look at this problem, we've got the natural log of the absolute value of cosecant x. Can cosecant x ever be negative? Well, you might think about it this way. Cosecant, that's not as familiar to us as the other way we can write it, which is what? 1 divided by sine x, okay? On the unit circle, is there any place where sine is negative? Yeah, keeping in mind that any point on the coordinate plane would be cosine theta, sine theta. And so, yeah, anywhere below the input axis, you'd have a negative sine value. And so if sine can be negative, can cosecant be negative? Yeah, and 1 divided by negative is negative. So that's where we would come up with then the absolute value here. So if I want the derivative with respect to x of the value, I'm going to put it in brackets here, natural log of cosecant x. Again, the parentheses are there, or the, excuse me, the absolute value signs are there because I want to make sure that I have a good value for the logarithm. Then this is going to be, well, once again, if we're talking about the derivative of a natural log, it always starts by being 1 divided by the quantity, and then because it's a function within a function, we have to use the chain rule. And so I'm just going to remind us by putting chain rule up here. We're going to use the chain rule. So this now has to be the derivative with respect to x of cosecant x. Now that derivative is not one that you will come across a lot. It's not one that I expect you to go home and memorize. I do expect you to know, though, the derivative of sine x. It's what? Cosine x. So if I were to take this and write cosecant x as 1 divided by sine x, could you find the derivative of 1 divided by sine x? Yeah. You could even find it using the chain rule. You could even find it as sine x to the negative 1 power. That would be the chain rule, of course, because we'd have to take the derivative of the outside function and then multiply times the derivative of the inside. But we could do that. Or you can go to the front of the textbook, or you can use your Inspire. You can do a lot of things to come up with the derivative of cosecant x. And we end up with cosecant 1 divided by cosecant x times, and that's going to be negative cosecant x cotangent x. And if we simplify that, we have negative cotangent x as our answer. So we're not really going to worry too much about those absolute values. It's just there to guarantee that we actually will have a derivative. Otherwise, if it's a negative quantity inside the natural log function, it's undefined, and we don't want to deal with those. Okay, next comes some slides that I'm going to talk about, but I'm not going to spend a whole lot of time with. One is this thing, the exponential function to base a. We are, the discussion I usually have with students on this is the whole thing of starting with a to the x power and showing that it in fact equals this quantity. Because then the next thing we do is take the derivative with respect to x of a to the x, and by using what we know about derivatives and all, we come up with our answer, or the value of this derivative as a to the x natural log of a. So I'm not going to go through all the steps that show why this is true. Again, I'm happy to do that with you, but I really feel compelled to move forward into some other material that we have instead of spending, it takes a little bit of time, in other words, to explain this, and I really don't know that everyone in here would appreciate the time we would take. So let's move on, if that's okay with you guys. But suffice it to say, we have this derivative, and we're going to see more of this in just a little bit. Same thing with this slide. The main idea of this slide is to just show that in fact the log of x base a is the same thing as 1 divided by, actually this one's not too hard to show. You probably did this back in trig class, where if you have, let's say, the log of, well, we'll just say x base 4. Now let's do this. Let's make it a number. The log of 3 base 4. And the reason we couldn't just put this in our calculators is because the operating systems on our calculators only had 2 logs in them. Natural log and common log. Natural log has base e and common log has base 10. So we didn't have any other way to do that. So what we'd said was this a statement like this can be rewritten as a log of 3 base anything divided by a log of 4 base anything. And it wasn't that hard to show why that is true, but do you remember this rule from trig class? Or from Algebra 2, maybe not trig, but maybe Algebra 2? No? Okay, well, it's there. Okay, it's changing. Now, that's not really necessary to us. We don't really need to do this because, well, the reason we would do it is we would say, well, let's use base 10. Now, do you have something in your calculator with base 10? Yes. So you could find out what the log of 3 base 4 is by changing it into a fraction using base 10. You could also do the natural log of 3 and the natural log of 4. I could have used the log base 20 if I wanted to. I mean, it doesn't make any difference what base I use as long as I use the same one. So this right here is saying nothing more than what I'm illustrating at this point, because this would be the same thing as the natural log of x divided by the natural log of a. Okay. Well, all of that is being said because we come up with this theorem. And on this theorem, a couple of things. One is, this is just, we already know this, the derivative of e to the x is e to the x. And we already know, because we've talked about it, that the derivative of natural log of x is 1 divided by x. We did that other lessons. It looks, though, as if in addition to those two, we've got 4 more things we have to memorize. And I'm just going to tell you, no, you don't. Of all 6 of these, including the 4, including the 2 that are highlighted, there's only 2 things that you really need to keep in mind. Now, let's start with the upper ones here. This is the derivative with respect to x of e to the x. What's your variable of differentiation? In other words, what's the input variable of your derivative? Yeah, the notation here tells you, down here is x. What is the input variable of your function? Well, it's x. Okay, so easy. Look down here, though. Same thing happening? Yeah, but the difference is this is of base e and this is of something other than base e. Now, the only rule we know is the one that has base e. That's the only thing we've been taught. That's the only base that we know for sure. And so we have something other than base e. And this is 2 slides ago we saw. This is the same thing as a to the x and then the natural log of a. So if we have something other than e, we do the same thing we do with base e. We write a to the x. We just then have to do something with that base, and we have the natural log of a. But keep in mind, we're still keeping this pretty simple. This would be something like, what's the derivative of 4 to the x power? What's the derivative of 7 to the x power? What's the derivative of pi to the x power? They're all to the x power. So take a look at this one. What's your variable of differentiation? X. What's the variable in your expression here? Yeah, it's something else. Now, that something else means then that that's like another function. This is like asking you to find the derivative with respect to x of, and let's make it 3 to the 4x squared plus square root x power. That's what this is equivalent to. Because we don't have base e, agreed? It's not base e, it's base 3. And we don't have just x up here, we've got another function. So it's a composite function. You've got a function within a function. You've got a function of that's the exponent within the function of exponential here. So what do? Well, same thing. A to the u power. So up here I would have 3 to the 4x squared plus square root x as my exponent. Times, well, I don't have e, so I've got to take the natural log of a. So times the natural log of 3.
You're almost at 5.
Thank you.